A visitor from a distant galaxy, designated Atlas, has crossed Mars' orbit and is now hurtling toward the Sunday at full speed, entering a critical phase of its interstellar journey. Early observations have revealed unusual phenomena. This celestial body is releasing vast quantities of water far from the Sunday, accompanied by diffuse gas clouds rich in carbon dioxide, a comet. Like tail, both characteristics strongly suggest its composition differs significantly from typical comets in our solar system. As Atlas approaches its closest point to the Sunday perihelion later this month, astronomers are closely monitoring its behavior. How will this object transform under the increasingly intense solar radiation? This video delves into the latest observational findings, analyzes their scientific implications, and explores potential future scenarios. Now, let's begin with the story of Atlas. In July, the Atlas Survey project in Hawaii first detected this faint object. Scientists quickly determined its velocity far exceeded the range of the Sunday's gravitational influence. Analysis of its trajectory confirmed a hyperbolic orbit, irrefutably proving its status as an interstellar visitor. Following Oumuamua, discovered in 2017, and Comet Borisov, discovered in 2019, Atlas became the third documented interstellar object. In early October, the comet crossed Mars' orbit. The trace gas orbiter Gaigio captured its distant image in time. The image reveals that Atlas possesses a bright condensed coma, but appears to lack a distinct coma. This phenomenon suggests that the behavior of this object may differ significantly from that of traditional comets we are familiar with. Spectral measurements from ground-based observatories and the James Webb Space Telescope provided crucial data. Analysis revealed that the object designated 3I Fe 2016 Chuai-4 is continuously releasing water vapor at a rate of approximately 40 kilograms per second. Despite being a staggering 29 astronomical units from the Sunday, such high activity remains exceptionally rare. Typically, most comets do not initiate such intense gas outbursts at such a distant location. Even more surprising is that the ratio of carbon dioxide to water vapor in its coma is the opposite of what is known for other comets. Water vapor is not the primary component, and carbon dioxide appears to be the main driving force behind its activity. Polarization measurements further corroborate this conclusion, revealing scattering patterns consistent with either fine dust particles or dust possessing unique chemical properties. Archival data from NASA's Transiting Exoplanet Survey satellite TESS also indicates early signs of activity for Atlas as far as 6 from the Sunday. This suggests its volatile substances began reacting before entering the inner solar system. This phenomenon is exceptionally rare, further indicating that its composition and thermal evolutionary history fundamentally differ from comets within our solar system. All evidence points to one conclusion: Atlas likely formed as a comet in a stellar environment entirely distinct from our solar system. One that may have been colder, possessed a more unique chemical composition, and was rich in volatiles far exceeding those typical of solar system comets. The scientific significance of these discoveries is extraordinary, as they challenge our long-held understanding of cometary behavior. Under typical conditions, water ice undergoes significant sublimation only within 3 astronomical units of the Sunday. Consequently, most solar system comets remain relatively inert before approaching the Sunday. Comet Atlas, however, breaks this rule. The prevailing explanation suggests that highly volatile compounds like carbon dioxide or deuterium may be buried beneath Atlas's surface, erupting at extremely low temperatures. The pressure generated by such eruptions could fracture the outer crust, allowing volatiles and water to escape earlier than anticipated. Another possibility is that Atlas's nucleus is unusually porous or riddled with numerous cracks, allowing sunlight to penetrate deeper and trigger early activity. Its chemical composition offers a unique window into the environments of other stellar systems. The dominant carbon dioxide signature suggests it likely formed in the colder outer regions of a protoplanetary disk around another star. This aligns with its interstellar trajectory, distinguishing it from typical solar system comets formed closer to the Sunday. Its polarization characteristics, how its dust particles scatter polarized light, also deviate from patterns common to our local comets. This suggests potential differences in the dust particle structure, size distribution, or mineral composition. Interstellar dust grains can carry chemical signatures from their parent star systems. So these data may help reconstruct the environment where Atlas was born. While speculative views, such as those proposed by A.V. Loeb, suggest that anomalous behavior in interstellar objects might point to artificial origins, the available evidence for the three-eyed Atlas points more strongly toward it being a naturally formed, volatiles, rich, and uniquely composed object whose characteristics were shaped by a distant stellar environment, alongside the previously discovered Oumuamua and Comet 2 I-Fabrasov. Atlas adds a third crucial data point to the emerging yet increasingly vital field of interstellar asteroid research. These objects act as messengers from other stellar systems, revealing how planetary formation unfolds across the Milky Way. The pivotal moment in Atlas's story is rapidly approaching. On the 3rd of October, it will reach perihelion, its closest point to the Sunday, at approximately 0.53 astronomical units. There it will endure the most intense solar radiation heating, which will determine its subsequent evolution. Astronomers anticipate three primary scenarios. 1. Activity surge. Intense solar energy may trigger a dramatic outburst, rapidly increasing the comet's brightness and forming a clearly visible tail 2. Disintegration. Like many volatiles, rich comets, it may fracture under thermal or rotational stresses, exposing its internal structure. 3. Smooth passage. A less probable outcome, but if Atlas remains intact, it will continue along its outer planetary orbit largely unchanged. The post-perihelion phase is critical for data collection. ESA's Jupiter Icy Moons Explorer, JUICES will monitor Atlas's evolution after perihelion from the Sunday's outer side. Since JUICE will employ its slower secondary antenna for observations at that time, results are expected in early 2026. Meanwhile, the James Webb Space Telescope, the Hubble Space Telescope, and numerous ground-based observatories will track its coma and spectral changes in near real time. If the comet survives, it will become visible from Earth again in early December, passing at a safe distance of approximately 270 million kilometers. By comparing Atlas's spectral data before and after perihelion, scientists can delve into how solar radiation alters this material originating from another star system. These invaluable data cannot be replicated in Earth-based laboratories. Their scientific significance extends far beyond this single celestial object. Atlas's arrival, like a new chapter in an interstellar encyclopedia, will help scientists refine models of interstellar debris exchange, revealing how material from distant stellar systems traverses the Milky Way and ultimately enters our galaxy. Understanding these interstellar objects provides crucial clues for comprehending planetary system formation, evolution, and interactions across cosmic timescales. Simultaneously, this presents an exceptional opportunity to enhance our capabilities for early detection and study of interstellar visitors. Each newly discovered interstellar object brings clear insights into their prevalence, composition, and behavioral patterns when exposed to solar radiation. With continuously improving observation and early warning systems, future interstellar comets may receive more detailed research, potentially even triggering dedicated flyby missions. Comet Atlas stands apart from our known comets, its unique chemical composition and early activity revealing valuable clues from other stellar systems. The transformations it undergoes during its upcoming perihelion may fundamentally reshape how we study interstellar visitors. For the past month, Earth's most powerful eyes, Hubble, James Webb, ground arrays from Atacama to Mauna Kea, have pivoted toward a single moving spark. We expected answers. Instead, the universe, with its usual mischievous grin, gave us harder questions and a deadline. In days, this visitor will slide behind the blazing curtain of the Sunday. When the lights come back up, it could be gone, its secrets receding into interstellar night for millennia. We call it 3I Atlas, Third Interstellar. In plain terms, it is not one of ours. It sailed in from another stellar neighborhood, perhaps an older, colder suburb of the Milky Way, carrying a chemistry kit we have never seen up close. We've only witnessed this class of traveler twice before. One, Oumuamua in 2017, the infamous shapeshifter that refused the comet's tail. And two, Divided by Borisov in 2019, a textbook comet that soothed our nerves just enough to be suspicious. Atlas is different. It's the third child who shows up and rewrites the family tree. Timeline first. Archival data show a faint point as early as the 7th of May, 2025, out beyond Jupiter's orbit flagged by TESS, a planet hunter that wasn't looking for comets at all. By July 1, the Atlas survey tagged it in real time between Jupiter and Mars, and the numbers started to sing. Hyperbolic speed, inbound on a sun-skimming arc, then outbound again by spring. Voyager took well over a year to reach Jupiter's distance. This thing ate that span in months. Conclusion, it's unbound. Gravity will bend its path, not capture it. A postcard tossed across the solar system, no return address. Now, the physics lesson and the first red flag. Classical comets are dirty snowballs. Water, ice laced with rock and organics. As they approach the sun, they sublimate solid to gas, forming a coma and tail pushed away by solar radiation and wind. The dog in a car window analogy holds, wind blows the fur back. Atlas breaks the script. Even when it was still beyond Jupiter, colder, dimmer, too far for water to lift, its brightness rose fast, as if outgassing had jumped the gun. That implies a different propellant. Carbon dioxide and carbon monoxide can sublimate in deep cold where water sleeps. Follow-up spectroscopy bears this out. A coma dominated by CO2, with water a minor player, roughly an 8-to-1 imbalance compared with the comets we cut our teeth on. Alien in the literal sense, forged under conditions not typical of our nursery. Then another oddity, structure in the coma and tail that at times seem to play tug of war with the Sunday. Tails should stream anti-solar. Jets and rotation can complicate the picture, yes, but some early frames hinted at a component oriented sunward, at least transiently. If confirmed, that invites explanations involving charged dust, solar wind interactions, and geometry, not violation of physics, but a reminder that nature loves edge cases. Shines sunlight through a cloud of grains, and you can read their shapes from how they polarize the light. Comets near small phase angles usually show a well-behaved negative polarization. Dip, small, modest, predictable. Atlas appears to push that phenomenon to extremes. The amplitude and angle shifts suggest grains that are fluffier, icier, more fractal, or outright different in composition than those in our backyard. It's the optical equivalent of a foreign accent. As Atlas brightened, models of the CO2 halo exploded in scale, hundreds of thousands of kilometers across a vast sunlit fog that could swallow planets whole. When the atmosphere is that big, inferring the size of the solid heart becomes like guessing a pearl from the shimmer of a fog bank. Early estimates ranged from a handful of kilometers to several tens. Recent fits allow an upper limit on the order of to 40-50 kilometers across. Not unprecedented, but coupled to that CO2 dominance, it points to an origin story far from our familiar recipe. Then came the metallic curveball. Spectra hinted at nickel emission in the coma without a matching signature of iron. In astrophysics, nickel and iron are twins, co-forged in stellar furnaces, traveling arm in arm through cosmic time. We see lots of both, rarely one without the other. Finding nickel lines devoid of iron is like opening a geode and finding piano wire. Could fractionation in extreme cold sort metals at grain surfaces? Could the lines be misattributed? Or the iron hiding in ionization states we didn't sample? Perhaps. But the anomaly sits there, tapping the blackboard. Here is the paradox that keeps dynamicists awake. Active comets usually show tiny, non-gravitational accelerations, whispers of thrust as jets fire from their sunlit seams. Atlas, despite a healthy coma, has shown little to none so far within measurement limits. One way to make thrust disappear is mass. A heavier nucleus shrugs off the jets. Another is symmetry. Vents firing in a near-balanced pattern cancel out. Each solution raises its own eyebrow. A massive CO2-rich nucleus would be an outlier among outliers. A perfectly symmetric jet network implies either uncanny luck or unfamiliar surface physics. Either way, the equation insists on something we don't yet understand. Because this is a once-per-decade laboratory experiment, nature runs for free. James Webb's infrared spectrometers read the molecule mix. Hubble resolves the coma's changing morphology. TESS and other wide-field eyes catch long baseline brightening trends. If there is structure at the core, lumps, lobes, or something jaw-droppingly geometric, Mars orbit cameras during the October pass were the best chance to glimpse a silhouette against the stars. We didn't expect glossy close-ups. We did hope to tease nucleus from cloud, to turn an argument into a measurement. When nature hands us a string of oddities, chemistry out of family, dust optics off template, thrust gone missing, the human mind does what it evolved to do. It sees patterns. Could a probe masquerade as a comet? Science fiction says yes. A heat-tolerant shell, a volatile skin to vent and confuse, a trajectory leveled into the ecliptic to sightline the planets like beads on a wire. Here is the scientist's answer. We must earn that conclusion. Extraordinary claims demand Not only extraordinary evidence, but ordinary discipline, multiple instruments, independent pipelines, predictions that can fail. Right now, Atlas sits in the interesting gray, consistent with a natural body born in a colder CO2-rich disk, provocative enough to keep alternative models on the whiteboard. The job is not to declare, it is to test. An 8:1 CO2-H2O ratio argues for formation beyond the CO2 frost line in its home system farther and colder than our Kuiper Belt's typical fare. The polarization anomaly hints at fragile, high porosity ice aggregates, snowballs of snowballs that shatter and scatter in unfamiliar ways. The nickel without iron puzzle, if it survives additional scrutiny, could mean surface processing in exotic radiation fields, grain scale sorting in deep cold, or something we haven't written down yet. With Atlas, every answer spawns a forked path. Each path is an invitation to refine planetary formation theory under alien conditions. Atlas swept Mars in early October, then knifed sunward to an October 29-30 perihelion, a moment of maximum heating, maximum drama, before vanishing behind the sun from Earth's line of sight. That blackout is celestial, not conspiratorial. Geometry can be cruel to curiosity. When it reemerges in November and December, the community will pounce. Did it flare, fragment, remain eerily intact? Did its course shift in ways we can't attribute to jets alone? These are the inexpensive, decisive diagnostics. Even as it heads outward, Atlas will thread the giant's domain. A March 2026 pass near Jupiter offers a coda, gravitational shearing that could tease structures in the coma, and if mission planners are nimble, opportunities for piggyback instruments to listen and look. Interstellar visitors don't RSVP. When they arrive, you redecorate your observing schedule. In science, maturity is not certainty. It is the ability to hold competing models in your head without flinching, to let nature arbitrate. Atlas is teaching us, again, that our comet taxonomy, water here, dust there, tidy tails, and textbook polarization was a parochial education. We trained on local kids. The galaxy is a big schoolyard. If Atlas is just a natural comet from a colder, older system, that is not a demotion, it is a gold mine. It is a sample return mission from another star without the price tag, a chemical Rosetta Stone telling us that planetary kitchens across the Milky Way stock different shelves. If, after the data flood, some anomalies refuse to die if the thrust stays missing, if the dust stays alien, even after we chase down every instrumental ghost, then we move the boundary markers. We write the proposal for instruments that could distinguish artifact in coma from comet in coma. We learn how to say, we were wrong, with a smile. For now, the clock runs. The sun will swallow our view. The messenger will reappear, changed by fire or unchanged in defiance. Between now and then, the task is clear. Reduce the rhetoric. Increase the signal. Archive the raw frames. Cross-calibrate the pipelines. Publish the null results as proudly as the headlines. Because once in a while, the cosmos tests not only our detectors, but our character. Do we cling to comfortable categories or widen them? Do we jeer at the unfamiliar or instrument it? Atlas is not just a rock or a riddle. It is a mirror. In it, we see what kind of civilization we are becoming. One that cancels anomalies or one that chases them. Stay curious. When the glare fades and the data return, we'll be here measuring, arguing, learning, and, with luck, adding a new chapter to the oldest story we tell. How small creatures on a small world learn to read the sky.
October 3, 2025. While NASA's Perseverance rover quietly captures a 20-frame stack of the Martian sky, the only sign of 3I Atlas, a verified interstellar visitor, is a faint, ambiguous smudge right where it should be. Yet just as the world demands answers and high-resolution orbiter images, nearly 15,000 NASA scientists are suddenly furloughed, and all official feeds fall silent. It's the perfect storm. Unprecedented anomalies, wild theories about a cylindrical object, and a blackout at the very moment the latest images reveal something strange about 3I Atlas. But what is being hidden, and why does every new claim seem to clash with what we thought we knew about interstellar objects? The story starts with a single blurry thread but unravels into something nobody expected. Within hours of the Perseverance stack surfacing online, a single frame, barely more than a faint blur, became the spark for a digital wildfire. Citizen astronomers pored over raw data, overlaying the predicted ephemeris of 3I Atlas against the Martian sky. The alignment was uncanny. The smudge fell exactly where the CNOS team said it should, yet the image's ambiguity proved irresistible. On X, users drew thick red ovals around the elongated feature, labeling it a cylinder or cigar, and urging others to enhance the pixels. Within a day, the meme had mutated. Now the object was a Martian monolith, a spacecraft, or a cosmic thumb drive. The original stack, a 20-frame composite, was dissected and reposted with every conceivable filter. Some threads claimed to spot surface markings, others insisted on a metallic sheen, and a few went so far as to trace supposed shadows, building a case for artificial geometry. Amateur sleuths began comparing the Perseverance data to older comet images, arguing that no known comet ever looked so perfectly straight. Each new repost added another layer of speculation, and soon the cylinder narrative drowned out technical explanations about cosmic ray hits or image noise. Astrometric overlays circulated in Discord science servers, with some users carefully matching the faint streak's angle to the predicted motion of 3I Atlas. The match was close enough to satisfy some, but for others, the lack of high-resolution orbiter images became the real mystery. Why, they asked, did the only available evidence come from a surface rover when Mars hosts a fleet of orbiters equipped with powerful cameras? As the meme gained traction, it drew in a wider network: space enthusiasts, skeptics, and conspiracy theorists alike. The absence of official imagery only fueled the fire. Each unanswered question was met with another viral post, and the boundaries between genuine inquiry and online spectacle blurred. In the vacuum left by silence, speculation flourished, and the demand for answers grew louder with every retweet.